Hello. Today we're going to talk about elastic potential energy. And that is the energy that we get when we stretch or compress anything that's elastic, like a spring or a rubber band. Okay. Uh, so a couple notes. For uh, a spring, we talked about the force of a spring. So force elastic is equal to Kx. So the farther you stretch a spring, the more force it takes. Um, the other thing that we've already learned is the equation for work. Work is a change in energy, okay? And the equation for work is force dot delta x, okay? And the units for work and energy, both, are joules, okay? So that's all review. Now, a couple notes. Let's talk about a spring for a second. Let's say you got a spring. Here it is, okay? And then let's say you grab the end of the spring and you pull it with some force. We'll call it a force of tension. Okay. Um, the spring will stretch out. All right. So I'll kind of draw an after picture. Okay, like so. All right. Now, while you were pulling the spring, there were two forces acting. There was you. That's your force of tension. You could also call it an applied force if you wanted to, pulling to the right. And the spring itself, force elastic, was pulling left. Okay. Now, there are two works being done here. The force of tension does positive work, and that is because that force is in the direction of the motion. You're pulling to the right, and that force acts to the right. Well, how about the spring? What sign of work is it doing? Well, its force is to the left while you're moving to the right. So the force is opposite the displacement. So this guy does negative work. Okay. So that's one thing you need to know is while you're stretching a spring, you're doing positive work on it and it's doing negative work. Okay. Now, here's the deal. You are doing positive work and giving the spring energy. The spring is taking that energy away, doing negative work. That energy has to go somewhere. Where did it go? Now, first of all, where did it come from? Well, it came from you, the food calories you ate today. When you pull on the spring, you give some food calories to do this work. So where does the energy go? Well, it goes into the spring itself. It is stored in the spring. And you know that because if you let that spring go, it can make something move. It can do something. It can do work for us, okay? So it turns out that there's energy stored in the spring. And that is what we call elastic potential energy. The symbol for that, we're just going to use an E for energy and then a little e for elastic, okay? Now, if you go look for this stuff online or in a textbook, there's a lot of other ways to write elastic potential energy. You may see it written this way, SPE. SPE stands for spring potential energy, okay? Same thing. You might also see it written this way, EPE. That's short for elastic potential energy. Same thing, okay? If you read a more advanced textbook or more advanced stuff, you might see U elastic. And U is a physics way of saying potential energy, and then the little e's for elastic. So you might see any of those, but for our worksheets and our stuff, we're going to use E sub E, energy elastic, okay? Now, we need to be able to calculate the elastic potential energy. Now, we have one issue. We know that work is force times distance, but in the previous discussions about springs, it turns out that you can't use that equation directly because as you stretch a spring, the elastic force changes. So you can't just take force times x because what force are you going to plug in? The force keeps changing, okay? So it turns out that there's a couple ways to calculate the energy stored in the spring. Now, a quick reminder from previous discussion, the slope of this line is the spring constant K, and the equation is F equals Kx. Okay, so K is the slope of that line. Okay. Now, let's just, for the sake of argument, let's throw some numbers on this graph. Let's say we had 0, 0, and then let's say here, let's say this was 10 centimeters, and that force is 20 newtons, okay? So for instance, if I wanted to find K, I would just take F divided by X. So K would be 20, and then X, we'd have to put 0.1 meters because you got to convert the centimeters to meters, and you would get K is 200 newtons per meter. Okay. So how do you figure out the energy stored in the spring? It's not a force. Force is not energy, and energy is not force. We use forces to get energy, but they're not the same thing. Okay. So how do we figure out the energy stored in the spring, or how much work we did to stretch it? Okay. Well, it turns out there's a couple ways. First way is if I ask you, or if you're asked to use the graph itself, you find the area of the graph, because the force is measured in newtons, and the stretch of the spring, if you measure it in meters, and if you take a newton times a meter, you get a joule, and that's the unit of energy. So it turns out that the area of the graph equals the elastic potential energy. Okay. So for this graph, the energy would be, if we did a numerical calculation, the energy would be 1/2. For a triangle, the area is 1/2 base times height. The base of the triangle is 10 centimeters or 0.1 meters, and the height of the triangle is 20 newtons. And you would get 1/2 of 2, which would be 1 joule exactly. Okay, so this spring would store exactly 1 joule of energy if you stretch it 10 centimeters. Okay. Now, it turns out there is a second way, which is going to be awfully convenient for most of our problems to determine the elastic potential energy stored in the spring. You don't always want to have to draw a graph and find an area. Okay, so what's another way to do this? Well, if you look at the area of the triangle, it's 1/2. The base of the triangle is simply x, and the height of the triangle is FE. But we have an equation for FE. That's equal to K times X. So I'm going to put that in for F. That's K times X. So this is 1/2 base times height, right? And if you put all that together, you get 1/2 KX squared. So the elastic energy stored in a spring is 1/2 KX squared. Now remember, K is a spring constant, and X is how far you stretch the spring. We can try it out for our spring really quick. We got 1/2. We figured out that the K value was 200, and we stretched this thing 10 centimeters, which is 0.1 meters, and we have to square that. And if you take 0.1 squared, you get 0.01. 0.01 times 200 is 2, and half of 2 is 1 joule. Okay, so it's often a lot easier to use this equation to determine the elastic potential energy in a spring. And again, that's the energy stored in the spring. All right, in our next video, I will do a few examples with this, and I wish you luck.